Sup, y'all. Today we're gonna be finding or solving, balancing a binary tree. So we're given a binary tree. We return true if it is height balanced and false otherwise. So that's right here. We're given a root and we just return true or false. And a height of a balanced tree, a height balanced binary tree is defined as a binary tree in which the left and the right subtrees of every node differ in height no more than one. So we can see that this one is balanced because the height of this is 2 and the height of this is 3. And 3 minus 2 would equal 1, and that's not more than 1. Let's go look at the other examples, try to get a good feel. So we can see that the height of the left subtree right here is 1. We see one edge, and this is 1, 2, 3. That's 3, so 3 minus 1 is 2, and 2 is actually greater than 1, right? So we know that that is returning false. We know that if the root is 0, then we go ahead and return true. Okay. First of all, let's go solve this by getting that base case. Say if if not root, we could go ahead and return true. That's this case right here. And now we could solve this using either depth first search or breadth first search. Let's try to solve this using depth first search. Okay. And some recursion is always good. So let's do that. So let's define depth first search. I think we should give it a tree, a new hello? Oh yeah. Yeah, making YouTube. I think we should give it a node for the depth first search. Just do that, right? And we should also get a height. And we could see that if the height differs from each one more than one, it's not balanced. Right, okay, let's go try to figure this out. Okay, let's go ahead and just check the first one. Let's see. If hmm, if not root, we could just return height. Hmm. Let's see, we gotta go on that left tree. See, we're on tree 2. How do we get the depth? I guess we could just traverse down this path, right? And we count that this is a depth of, let's see. Yeah, we could traverse down this path. See, it's a depth of 1. This is a depth of 2, then subtract. Guess we get the max height of both. Yeah. Okay, we could do that. Subtract the difference. Okay. Okay, how do I find the end? How do I get the height? How do I get the height? To get height, we can use max function. Right, the max height of this is one, max height of that's two, max of this is one, max of this is three. We could say something like call itself. We could return if not root, return zero. Def for search on node left. We could give its current height would be, I guess, zero. And I guess we could put a comma and just say run it again on the right node and get the max of this. No, yes. We gotta do like plus one though. Would this work? Would that work? I don't think it would. Hmm. Each time we call the method, I'm thinking it's like one, right? Then that increment could be the height. Select DFS, right? Like on negative one position plus one, that'd be whack. And then I would just say, just return max. No, this would be like return for search. Max, left, root, dot, minus, differ search, min of, hey, this is like theoretically some booth code. Oh, it's gonna be bad, but let's see. Oh shit, okay. Oh yeah, it's like 1 versus 6. Okay, I see. Damn, okay. I think depth first should have a height, right? We should have something to hold height, right? See the solution. Left equals depth first search node left. How's that work? I just try to understand the solution here. Brute force, depth first search, iterative depth first search. All right, let's do regular recursive depth first search. It's this, okay. Okay. Define def for search root. If it's not, we'll return true and zero. Ah, okay, I got that part right. We should have something to hold true. Keep on calling as long as true. If number root. Damn. Left is equal to def for search left. So I'll just keep on calling left until we reach the leaf node. Balance is equal to left and right. Left 0. So it has to be true. Okay, hold on. Let me just write this out. If not, node return guess true. If the node is there, return 0. Depth is 0. This means that there is no children. Okay, I think that's what it means. I would say left. Let's go to def for search. Roots dot left. Oh, actually, they call it node in my situation. Right is equal to def for search. Node dot right. Okay, I gotta kind of figure out this place. Left is equal to def for search node left. What does this do? So let's say left calls left is equal to def for search node left. What is this gonna equal this? This is 0, man. Doesn't it equal that 0? I feel like it will, right? Do I got this part right? I don't know. Okay. Damn. Indentation's wrong. Yeah, it's already wrong. Okay. Yes. We go deep first. Okay. Now balanced is equal to left 0. Okay, so equal to true. This is the true. This is the true and right and left. Minus 1 less than or equal to 1. Okay, it's kind of just checking, right? Checking if they're both true. Okay. Now this recursive function. Okay. Turn balanced. Oh, this is going to either be true or false, right? This is so true, true. Yeah, these are all true, true, falses. Okay, so three true falses, three Boolean values. And then we return balanced. So, okay. Then 1 plus max left. Ah, okay. Again, that right one, which is always going to be 0. Return balanced. Okay, so that's this. Then max left 1. Okay, so left 1. Hmm. I think that's what this is explaining right here. Okay. Hmm. Height is equal to 1 plus max 0, 0. True. Okay. Left is true. True. think I kind of got it. Still, I definitely need more practice when it comes to recursion. I'm gonna go work on that. But yeah, I think this should be the solution now. Yeah, I'll definitely have to come back to this question later when I'm more experienced. Then again, thank you guys for watching.